Introduction. Hydraulic machines are defined as those machines which convert either hydraulic energy into mechanical energy, which is further converted to electrical energy, or mechanical energy into hydraulic energy. Hydraulic machines are of two types: turbines, pumps. SCTE and VT, Odessa of fluid mechanics and hydraulic machines. 93. Turbines. Turbines are defined as the hydraulic machines which convert hydraulic energy into mechanical energy. This mechanical energy is used in running an electric generator, which is directly coupled top the shaft of Teague turbine. Thus mechanical energy is converted into electrical energy. The electrical power, which is obtained from the hydraulic energy, is known as hydroelectric power. Classification of hydraulic turbine. Hydraulic turbines are classified: 1. According to the type of energy at inlet. A. Impulse turbine. The energy available at inlet is only kinetic energy. B. Reaction turbine. The water passes kinetic energy as well as pressure energy at the inlet of the turbine. 2. According to the direction of flow through runner. A. Tangential flow turbine. Water flows along the tangent of the runner. B. Radial flow turbine. Water flows in the radial direction through the runner. C. Axial flow turbine. Water flows through the runner along the direction parallel to the axis of rotation of the runner. D. Mixed flow turbine. Water flows through the runner in the radial direction, but leaves in the direction parallel to axis of rotation of runner. 3. According to the head at the inlet of turbine. A. High head turbine. B. Medium head turbine. C. Low head turbine. 4. According to the specified speed of turbine. A. Low specific speed turbine. B. Medium specific speed turbine. C. High specific speed turbine. SCTE and VT, Odessa of fluid mechanics and hydraulic machines. 94. Definitions of heads and efficiencies of a turbine. 1. Gross head. The difference between the head race level and tail race level when no water is flowing is known as gross head, Hg. 2. Net head. It is also called effective head, and is defined as the head available at the inlet of the turbine. When water is flowing, a loss of head due to friction between the water and penstocks occurs. So net head equals Hg, Hf. Hg equals gross head. Hf equals head loss due to friction. Equals, where V equals velocity of flow in penstock, L equals length of penstock, D equals diameter of penstock. 3. Efficiencies of a turbine. The important efficiencies of a turbine are: A. Hydraulic efficiency. B. Mechanical efficiency. C. Volumetric efficiency. D. Overfill efficiency. A. Hydraulic efficiency equals Wp equals water power equals times Kw. SCTE and VT, Odessa of fluid mechanics and hydraulic machines. 95. W equals weight of water striking the vanes of the turbine per second. Equals Wp equals times Kw. For water equals 1000 kg/m3. B. Mechanical efficiency equals The Peltron wheel or Peltron turbine is a tangential flow impulse turbine. The water strikes the runner along the tangent of the runner. The energy available at Teague inlet of the turbine is only kinetic energy. The pressure at the inlet and outlet of the turbine is atmosphere. This turbine is used for high heads. Constructions. The main parts of the Peltron turbine are nozzle and flow regulating arrangement, runner and buckets, casing, braking jet. 1. Nozzle and flow regulating arrangement. The amount of water striking the buckets of the runner can be controlled by providing a spear in the nozzle. The spear is conical and operated by hand wheel. SCTE and VT, Odessa of fluid mechanics and hydraulic machines. 97. When spear is pushed forward, the amount of water striking is reduced, and when spear is pushed back, the amount of water striking the runner is increased. SCTE and VT, Otis of Fluid Mechanics and Hydraulic Machines. 98. 2. Runner and buckets. The runner of the peltron will consists of a circular disc on the periphery of which a number of buckets evenly spaced are fixed. The shape of the bucket is of a double hemispherical cup and bowl. Each bucket is divided into two symmetrical parts by a dividing wall which is known as splitter. The buckets are made of cast iron, cast steel, bronze, or stainless steel depending upon the head at inlet. The splitter divides the jet into two equal parts, and the jet gets deflected through 1,600 or 1,700. 3. Casing. The function of the casing is to prevent the splashing of the water and to discharge water to tail race. It is made of cast iron or fabricated steel plates. 4. Braking jet. When the nozzle is completely closed by moving the spear in forward direction, the amount of water striking the runner reduces to 0. But due to inertia, the runner goes on revolving for a long time. To stop the runner in short time, a small nozzle is provided which directs the jet of water on the back of the vanes. This jet is called braking jet. SCTE and VT, Otis of Fluid Mechanics and Hydraulic Machines. 99. Velocity triangles and work done for peltron wheel. The jet of water strikes the bucket at the spitter. 103. Francis Turbine is an inward flow reaction turbine, having radial discharge 80 outlet. Radial flow reaction turbine. Radial flow turbines are those turbines in which the water flows in the radial direction. The water may flow radially from outward to inward or from inward to outward. Reaction turbines means that the water of the inlet of the turbine poses kinetic energy as well as pressure energy construction. And parts of a radial flow reaction turbine. The main parts of a radial flow reaction turbine are 1. Casing. 2. Guide mechanism. 3. Runner. 4. Draft tube. SCTE and VT, Otis of Fluid Mechanics and Hydraulic Machines. 104. Casing. In CSE OIF reaction turbine casing and runner are always full of water. The water from the penstocks enter the casing, which is of spherical shaft in which are of cross-section of the casing goes on decreasing gradually. The casing is made of concrete, cast steel or clat steel. Guide mechanism. It consists of stationary circular wheel all roomed of the turbine. The stationary quid bench are fixed on the guide mechanism. The guide vanes allow the water to strike tie vanes fixed on the runner without shock at inlet by watering the adjacent vanes of guide mechanism. The amount of water striking the runner can be varied. Runner, it is a circular wheel on which a series of radial curve vanes are fixed. The radial curve vanes are so shaped that the water enters and leaves the runner without shock. The runners are made up of cast steel, cast iron, or stainless steel. They are keyed to the shaft. DRFT tube. The pressure at the exit of the runner of a reaction turbine is generally less than the atmospheric pressure. The water at exit cannot be directly discharged to the tail race. A tube or pip, of gradually increasing area, is used for discharging water from the exit of the turbine to the tail race. This tube of increasing area is called draft tube. Inward flow reaction turbine. In this case, the water flows from outward to inward through the runner. In this case, the water from the co-song enters the stationary guide wheel. The guiding wheel consists of guide vanes which direct the water to enter the runner, which direct the water to enter the runner, which consists of moving vanes. The water flows over the moving vanes in the inward radical direction and is discharged at the inner diameter of the runner. The outer diameter of the runner is the incept and the inner diameter of the runner is the outlet. SCTE and VT, Otis of Fluid Mechanics and Hydraulic Machines. 105. Velocity triangle and work done. The work done per second on the runner by water for radially curved vanes is V1 plus or minus. The above equation also represents the energy transfer per second to the turbine. If the water flows from inward to outward through the runner, then that turbine is known as outward flow reaction turbine. In this case, at inlet of the runner is at the inner diameter of the runner, the tangential velocity at inlet will be less than that of at outlet. U1, U2 as D1, D2 the velocity triangles at inlet of outlet, work done by water on runner per second, the horsepower developed, the hydraulic efficiency is similar as inward flow reaction turbine. SCTE and VT, Odessa of fluid mechanics and hydraulic machines. 109. Francis Turbine. The inward flow reaction turbine, having radial discharge at outlet, is known as Francis Turbine. The water enter the runner of the turbine in radial direction at outlet, and leaves in the axial direction at inlet of the runner. So the modern Francis Turbine is a mixed flow type turbine. Axial flow reaction turbine. If the water flows parallel to the axis of the rotation of the shaft, the turbine is known as axial flow turbine. For axial flow reaction turbine, the shaft of the turbine is vertical. The lower end of the shaft is made larger, which is known as hub or boss. The vanes are fixed on the hub, act as a runner for axial flow reaction turbine. Types of axial flow reaction turbine. 1. Propeller turbine. When the vanes fixed on the hub are not adjustable, the turbine is known as propeller turbine. 2. Kaplan turbine. When the vanes fixed on the hub are adjustable, the turbine is known as Kaplan turbine. Kaplan turbine. SCTE and VT, Odessa of fluid mechanics and hydraulic machines. 110. 1. When the vanes fixed on the hub are adjustable, the turbine is known as Kaplan turbine. 2. This turbine is suitable where larger quantity of water at low height of available. 3. Kaplan turbine consists of a hub fixed to the shaft. 4. On the hub the adjustable vanes are fixed. Main parts of a Kaplan turbine. 1. Skull casing. 2. Guide vanes mechanism. 3. Hub with vanes or runner of the turbine. 4. Draft tube work. MG1. The water from penstock enters the scroll chasm and then moves to the guide vanes. 2. From the guide vanes, the water turns through 900 and flows axially through the runner. 3. The discharge through the runner is given by 4. The outlet and inlet velocity triangles are drawn at the extreme edge of the runner and similar as reaction turbines. SCTE and VT, Odessa of fluid mechanics and hydraulic machines. 111. Important points for Kaplan turbine. 1. The peripheral velocity at inlet and outlet are equal. 2. Velocity of flow at inlet and outlet are equal. 3. Area of flow at inlet equals area of flow at outlet. Governing of turbines. 1. The governing of a turbine is defined as the operation by which the speed of the turbine is kept constant under all condition of working. 2. By means of a governor the rate of flow through the turbine is automatically regulated according to the changing load conditions on the turbine. 3. Governing is necessary as a turbine is directly coupled to an electric generator, which is required to run at constant speed under all fluctuating loads condition. 4. This is only possible when the speed of the generator under all changing load condition is constant, and for that the speed of the turbine should be constant. 5. If the turbine or the generator is to run at constant speed, the rate of flow of water to the turbine should be decreased till the speed becomes normal. 6. This process by which the speed of the turbine, or kept constant under varying condition of load, is called governing. Draft tube. 1. Draft tube is a pipe of gradually increasing area which connect the outlet of the runner to the tail race. 2. It is used for discharging water from the exit of the turbine to the tail race. This pipe of gradually increasing area is called draft tube. 3. One end of the draft tube has the following two purposes. 4. It permits a negative head to be established at the outlet of the runner, and thereby increase the net head on the turbine. The turbine may be placed above of the tail race without any loss of net head, and hence turbine may be inspected properly. 5. It converts a large proportion of the kinetic energy, V2/2G, rejected at the outlet of the turbine, into useful pressure energy. Without the draft tube, the Ke rejected at the outlet of the turbine will go waste to the tail race. SCTE and VT, Odessa of fluid mechanics and hydraulic machines. 112. Types of draft tube. 1. The flowing are the important types of draft tubes which are commonly used. I. Conical draft tubes 2. Simple elbow tubes 3. Moody spreading tubes 4. Elbow draft tubes with circular inlet and rectangular outlet. Criteria for selection of hydraulic turbine. The main selection criteria of hydraulic turbine is specific speed. Also, the performance of a turbine can be predicted by knowing specific speed. Types of turbine for different specific speed. Type of turbine specific speed M.K.SSI Pelton, wheel with single jet 10 to 35 85 to 30 Pelton, wheel with 2 or more jet 35 to 60 30 to 51 Francis Turbine 60 to 351 to 225 Kaplan or Propeller Turbine 300 to 1255 to 860. Specific speed. It is defined as the speed of a turbine which is identical in shape, geometrical dimensions, blade angles, gate openings, etc., with the actual turbine, but of such a size that it will develop unit power when working under unit head. It is denoted by the symbol NS. The specific speed is used in comparing the different types of turbine, as every type of turbine has different specific speed. SCTE and VT, Odessa of Fluid Mechanics and Hydraulic Machines. 113. Numerical problems. 1. Quetzal. A platen wheel has a mean back-at speed of 10 mt. Definition and classification of pumps. 8.2 Centrifugal pumps. Construction and working principles, velocity diagram of a single impeller, work done, and efficiency. Numerical problems. Concept of multistage centrifugal pumps. Cavitation causes, and its effect. 8.3 Reciprocating pumps. Construction and working principle of single-acting and double-acting reciprocating pumps. 8.4 Concept of slip and negative slip. The hydraulic machine, which converts mechanical energy into hydraulic energy, are called pumps. The hydraulic energy is in the form of pressure energy. The pumps are of two types. 1. Centrifugal pump. 2. Reciprocating pump. SCTE and VT, Odessa of Fluid Mechanics and Hydraulic Machines. 115. Centrifugal pump. The centrifugal machine, which converts mechanical energy into pressure energy by means of centrifugal force acting on the fluid, is known as centrifugal pump. The centrifugal pump acts as a reverse of an inward radial flow reaction turbine. The centrifugal pump works on the principle of forced vortex flow, which means that when a certain mass of liquid is rotated by an external torque, the rise in pressure head of the rotating liquid takes place. The rise in pressure head at any point is proportional to the square of tangential velocity of the liquid at that point. I.e. V2/2g or W2R2/2g. Main parts. The main parts of a centrifugal pump are 1. Impeller. 2. Casing. 3. Suction pipe with a foot valve and strainer. 4. Delivery pipe. SCTE and VT, Odessa of Fluid Mechanics and Hydraulic Machines. 116. 1. Impeller. The rotating part of a centrifugal pump is called impeller. It consists of series of backward curved vanes. The impeller is mounted on a shaft which is connected to the shaft of an electric motor. 2. Casing. The casing of a centrifugal pump is similar to the casing of a reaction turbine. It is an airtight passage surrounding the impeller. It is designed in such a way that the kinetic energy of the water discharged at the outlet of the impeller is converted into pressure energy before the water leaves the casing and enters the delivery pipe. There are 3 types of casing are commonly used. I. Volute casing. 2. Vortex casing. 3. Casing with guide blades. Volute casing. It is a spiral type in which area of flow increases gradually. The increase in area of flow decrease velocity of flow, and decrease in velocity increases the pressure of the water flowing through the casing. Vortex casing. If a circular chamber is introduced between the casing and impeller, the casing is called vortex casing. By introducing the circular chamber, the loss of energy due to the formation of eddies is reduced to a considerable extent. Thus the efficiency of the pump is more than the efficiency when only volute casing is provided. SCTE and VT, Odessa of Fluid Mechanics and Hydraulic Machines. 117. Casing with guide blades: the casing in which the impeller is surrounded by a series of guide blades mounted on a ring, which is known as diffuser. The guide vanes are designed in such a way that the water from the impeller enters the guide vanes without shock. Also, the area of the guide vanes increases, thus reducing the velocity flow through guide vanes, and consequently increasing the pressure through the surroundings casing, which is in most of the cases concentric with the impeller. SCTE and VT, Odessa fluid mechanics and hydraulic machines. 118. 3. Suction pipe with a foot valve and a strainer, a pipe whose one end is connected to the inlet of the impeller and other end dips into the water in a sump, is known as suction pipe. A foot valve, which is a non-return valve, or one-way type of valve, is fitted at the lower end of the suction pipe. It will open only upward direction. A strainer is also fitted to filter the water. 4. Delivery pipe, the pipe whose one end is connected to the outlet of the pump and other end delivers water at a required height, is known as delivery pipe. Work done by the centrifugal pump on water. In case of centrifugal pump, work is done by the impeller on the water. The water enters the impeller radially at inlet for best efficiency of the pump, which means the absolute velocity of water at inlet makes an angle of 90 with the direction of motion at inlet. Hence equals 90 degrees, VW1 equals 0. SCTE and VT, Odessa fluid mechanics and hydraulic machines. Fluid mechanics and hydraulic machines. 120. Definitions of heads and efficiencies of a centrifugal pump. 1. Suction head, HS. It is the vertical height of the center line of the centrifugal pump above the water surface in the tank or sump from which water is to be lifted. This height is also called suction lift. 2. Delivery head, HD. The vertical distance between the center line of the pump and the water surface in the tank to which water is delivered is known as delivery head. 3. Static head, HS. The sum of section head and delivery head is called static head. It is written as HS equals HS plus HD. 4. Manometric head, The manometric head is defined as the head against which a centrifugal pump has to work. A equals head imparted by the impeller to the water, loss of head in pump. If a centrifugal pump consists of 2 or more impellers, the pump is called a multistage centrifugal pump. The impeller may be mounted on the same shaft or on different shaft. A multi-stage pump is having 2 functions, I. To produce a high head, 2. To discharge a large quantity of liquid. If a high head is to be developed, the impellers are connected in series, while for discharging large quantity of liquid, the impellers are connected in parallel. Multi-stage centrifugal pump for high heads. For developing a high head, a number of impellers are mounted in series or on the same shaft. The water from suction pipe enters the first impeller at inlet, and it discharges at outlet with increased pressure. The water with increased pressure from the outlet of the first impeller is taken to the inlet of the second impeller with the help of connecting pipe. At the outlet of the second impeller, the presence of water will be more than the pressure of water at the outlet of the first impeller. Thus, if more impellers are mounted on the same shaft, the pressure will be increased further. N equals no. Of impeller mounted on the same shaft. Equals head developed by each impeller. Total head developed equals N times SCTE and VT, Odessa fluid mechanics and hydraulic machines. 125. Multi-stage centrifugal pump for high discharge. For obtaining high discharge, the pumps should be connected in parallel. Each of the pumps lifts the water from a common sump and discharges water to a common pipe to which delivery pipe of each pump are connected. Each pumps is working against the same head. N equals number of identical pumps are in parallel. Q equals discharge through each pump. Total discharge equals N.Q. SCTE and VT, Odessa fluid mechanics and hydraulic machines. 126. Priming is a centrifugal pump is defined as the operation in which the suction pipe, casing of the pump, and a portion of the delivery pipe to the delivery value is completely filled up from outside source with the liquid to be raised by the pump before starting the pump. Thus air from these parts of the pump is removed and these parts are filled with the liquid to be pumped. The work done by the impeller equals the head generated by the pump equals. It is independent of the density. So when the pump is running in air, the heat generated is in terms of meter of air. If the pump is primed with water, the head generated is same meter of water. But as the density of air is very low, the generated head of air in terms of equivalent meter of water head is negligible. And hence the water may not be sucked from the pump. To avoid this difficulty, priming is necessary. SCTE and VT, Odessa Fluid Mechanics and Hydraulic Machines. 127. Comparison between centrifugal pump and reciprocating pump. Centrifugal pump, reciprocating pump. The hydraulic machine, which converts mechanical energy into pressure energy by means of centrifugal force acting on the fluid, is called centrifugal pump. The hydraulic machine, which converts hydraulic energy into pressure energy by sucking liquid in a cylinder in which piston is reciprocating, known as reciprocating pump. It occupies less floor space. It occupies 6 to 8 times more floor space area than centrifugal pump. Installation is easy. Installation is difficult. Maintenance cost is less. Maintenance cost is high. It requires priming. It does not require priming. It is suitable for large discharge and small head. It is suitable for low discharge and high head.